This is lesson 9.6, where we're going to talk about the integral tests and the p-series tests. Now, remember back in, I think, lesson 9.3, where we talked about convergence and divergence of series? Yeah, so we're going to go back to that kind of theme for the later half of this unit. And I want to show you some other tests that you can use to help determine if something is converging or diverging. Remember, the idea of converging is that the series actually converges to an actual number, so it's a finite sum, where if it diverges, the sum is infinity or near infinity. Now, in this lesson, I want to talk about the integral test first. And this is one where if you have a function, f of x, and these are the conditions, okay? Positive, it's continuous, and it's decreasing for x being bigger than 1. And the terms can be represented by a function, then what we're saying is that the sum of n equals 1 to infinity of a sub n, so that's the infinite series of those terms, and this, the integral from 1 to infinity of the function f of x dx, they either both converge or they both diverge. So really what you need to do here is take or calculate this integral. And if the integral converges to a number, then you know that series does as well. If the integral goes and diverges, then you know that series does as well. Okay? Now, I need you to understand this though. Okay, this note. The series does not equal to the integral. Okay? We're just saying that the integral can be used as a test to determine if it's convergent or divergent. It doesn't say that the integral response or the result is equal to the actual sum of the series. Okay? Now, once again, just to be aware, if they ask you for the required conditions, then you need to state these three things. Okay? Positive, continuous, and decreasing. Those are the three conditions. Okay? So let's try these out. Okay? Here's example 1 and 2. Use the integral test here to determine the convergence or divergence of these sums. Okay? So really I'm asking you to do the following. Can you take the integral from 1 to infinity of this expression? Now remember, going to infinity is not really a real proper integral, it's an improper integral. And remember how we introduced this notation b, where b goes to infinity? Yeah, you need to do that here again. And our function is not 1 over n squared. I'm just going to replace n with x. So we have our more typical function in terms of x. And now I'm going to ask you, what is the antiderivative of 1 over x squared plus 1? Oh boy, do you remember these antiderivatives from your AB course? I hope so. And if you didn't, I'll tell you what this is right now. Once again, we still have the limit as b approaches to infinity. This becomes arctangent of x. And yes, we need to evaluate this from b to 1. So I will continue to write down limit b approach to infinity, arctangent of b minus arctangent of 1. And then if I plug in infinity to the arctangent of b, think about what angle that gives me. That must be one of those vertical asymptotes. So this whole thing just becomes pi over 2. The arctangent of 1, that's, I believe, pi over 4. So pi over 2 minus pi over 4 is pi over 4. This is a number. So therefore, the series converges by the integral test. And the short form for that would be IT. All right, so you try number 2. Same idea, right? Integral from this time 2 to infinity, so it doesn't always have to start at 1. It can start at any actual number. Okay? 1 over n ln n. This is interesting. So I'd be like 1 over x ln x dx. And I'm thinking this is very interesting because I can see already that this is u substitution. Oh, du dx is 1 over x, or dx equals to x du. Oh boy. So if I were to do that, I'm just going to deal with this right now. This becomes, I believe, 1 over u du. And if I take the antiderivative of that, that just becomes, so I'm going to write this now as the limit of b approach to infinity. That just becomes what? Natural log, right? So that's natural log of absolute value of u. So I'm going to write this as natural log of the absolute value of natural log of x. And we're going to evaluate this from b to 2, or 2 to b. Okay? And once again, let's just plug this in. Natural log of b minus natural log of 2. We know this is just a number constant. This, however, when I plug in infinity, gives me infinity. So infinity minus a number is still going to be infinity. So therefore this diverges by the integral test. Okay. All right. So that's how you do this. And I'm going to ask you now to try the next 3 examples, 3, 4, and 5, because I think you can do this now. You don't really need me. Okay, you can do integrals. You can tell if it's a number or infinity and tell me if it's converging or diverging. All right? So I'm going to ask you to press pause. You know that famous pause. And try these yourself. And then once you're done, come back and check the answers with me. Okay? All right then. Press pause. What's this integral? Got it. Natural log. Absolute value of x. Going from 1 to b. Limit b approach to infinity. Natural log of x. Ooh, what happened there? Natural log of the absolute value of b minus natural log of 1. I think that just means natural log of infinity, which of course equals to infinity. Therefore, this diverges. So therefore, the series diverges. Once again, by the integral test. Number 4. Limit b approach to infinity. Integral from 1 to b of 1 over root x dx. Once again, that is the same thing as x to the negative 1 half. So if I take the antiderivative using power rule, x to the positive 1 half divided by a half integral from 1 to b, or if I were to plug this in and say 2x to the 1 half from integral from 1 to b, we get here the limit of b approach to infinity 2 root b minus 2. And if I plug in infinity here, this also becomes infinity. So therefore, this series diverges by the integral test. Okay? So notice in example number 3, 1 over x is what? X to the negative 1. That diverges. X to the negative 1 half. This one also diverges. And let's take a look at number 5. Same idea. Do you think this diverges too? Well, let's find out. That's x to the negative 2. So if I take the antiderivative of that, what happened? If I take the antiderivative of that, x to the negative 1 over negative 1, 1 to b, negative 1 over b, minus, what's this, negative 1 over 1, negative 1. So now if I plug in b going to infinity, this term becomes 0, and I go 0 plus 1. That's 1. Whoa! It's not infinity. So therefore, this series converges by the integral test. Interesting. 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 This gives rise to something that I want to talk about next, which is called the p-series. Notice that p in this case is a positive constant that's written in this form, where it's 1 over n to the power of p. So if you look at example number 3, I hope you can see that p is equal to, that's right, 1. And if you look at example number 4, what's p equal to? That's right, p equals to half, okay, because we're looking at it already in the denominator. And then finally, for number 5, what is p? P is equal to 2. Well, all 3 of the examples were p-series. And what I'm saying to you is each of those could be done with the following test. Yes, we have something called the p-series test. And what it's saying is if p is bigger than 1, once again, the value of p is already in the denominator. It's the exponent that's already in the denominator. Then the p-series here converges, which is exactly what I had for number 5, right? P is equal to 2. Yet the other two, 1.5, guess what? If the p-series is less than or equal to 1 and bigger than 0, then it diverges. Okay? Now there is a special series. The number 3 example here, where I had 1 over n, that's a special series called the harmonic series, where p is equal to 1. And that one, interestingly enough, yes, it diverges. Okay? So if you can write the terms as a p-series, then you don't have to do integral tests. You can just quote the p-series test, and boom, get the answer. So looking at these last 2 examples for this lesson, use the p-series test to determine convergence or divergence of these series. So key thing is, can you write them as a p-series? Doesn't this kind of look like 2 to the power of 3 halves? Doesn't this look like 1 over 3 to the power of 3 halves? Doesn't this like 1 over 4 to the power of 3 halves? Yeah, so really I can rewrite this as the summation of n equals to 1 to infinity of the expression 1 over n to the power of 3 halves. And therefore, I see that this is in the p-series form because it's 1 over something to the power. Note, in this case, the p-value is actually equal to 3 halves. And then since this p-value is bigger than 1, by the p-series test, we know this converges. Okay. So for number 7, looks ugly, but if we can rewrite it as a p-series, we're good. So can we rewrite this as a p-series? Let's see if you can combine it together and cube. Ooh, what's this? The cube root. Remember how we can write this as negative 11 over 3? Yes. And then if I were to now combine these together, what do we get? Uh-huh. Exponents, multiplication. We add them together. What's 3 plus negative 11 over 3? That's, I believe, 9 over 3 minus 11 over 3. That's negative 2 over 3. So n to the power of negative 2 over 3, which as a p-series, once again, yes, we have to rewrite it so that it's 1 over n to the power of positive 2/3. In this case, our p-value is 2/3, which is less than 1. So yes, this diverges by the p-series test. That's it. Now get to work.